right, so as we get started, today's least surprising development is that the Tuesday lecture during an exam week is sparsely populated. So for those of you that are here, thank you for your dedication. It will go a long way to ensuring your success in this course. Today's lecture is fairly important because we're going to finish chapter 4, which would be all covered on this week's homework assignment. And then they're going to see, starting on Thursday, a pretty big transition in terms of the types of things we're covering. But today we have one more thing to do related to molecular structure, molecular bonding, and so that's what's going to be covered. All right, so first though we have the usual thing about what we call Try Hard Tuesday, work habits and things. So what I looked at this week was, we've talked a lot already about how many homework attempts we're doing and the importance that that has on your success in the course. But I also want to take a little bit of a deeper dive and look at when we're doing the homework assignment attempts, because I think that's also fairly telling. Not terribly surprising, but some things that I think we can improve on. So for the Chapter 3 homework that was just due on Sunday, there were 571 total attempts out of about 214 students, so that's roughly 2.5 per student. So again, we could do better on that. We've already talked about that issue for some people already. But I think when we do the homeworks is particularly interesting. So between the Sunday that it opened up and Saturday, which was the day before it was due, there were 187 attempts. And on Sunday, the 19th, the day that it was due, there were 384. So a little bit of quick percentages. That means 2/3 of the attempts were completed on the last day. And moreover, 41% of the total attempts were completed after 6 p.m. on the last day. So basically, the last 6 hours that it was due out of 8 days that it's open. So, I was a college student once. So I understand that things often get put off until the last minute. I'm not that naive, but I do think I want to encourage you all to consider doing some of your attempts at least earlier in the week. And there's advantages to that, which I've talked about a little bit. But what a lot of the students do in this class that do particularly well is they try some of their homework attempts earlier in the week. And we also have ungraded preview attempts as well, if you've looked at that part of it too. So you can even do some of them ungraded to get a little bit of a hang of what you're doing before the graded attempts. But some combination of either ungraded or graded attempts earlier in the week, and then throughout the week, either from me in office hours or your favorite tutor at a tutoring or review session, you can get help on the difficult problems, and then in the later attempts you can kind of test yourself to see, okay, did I actually learn this topic and understand it as well as I thought I did? So it's a good way of testing yourself throughout the week. It also avoids burnout. Our homework assignments don't take that long, but if you're trying to cram in 4 attempts at 10 p.m. on a Sunday night, that's probably not the best for avoiding burnout. So I would encourage you to spread them out more. And then I think, just as we've kind of been emphasizing throughout the semester in general, for learning well in this class, a little bit of effort every day is a lot better than a feast or famine approach where you spend a lot of time one day and then kind of drop it and forget about it for a few days. So spreading out the effort in all ways, whether it's homework assignments or otherwise, I think is helpful and will make you more likely to retain information and feel better prepared for exams when they come up. So that's my suggestion for the week. I hope I'll see improvement in that regard. I'm not expecting to necessarily, but now you guys know, so hopefully that'll spur some of you to change your habits a little bit. All right, but on to what we're going to cover today, which is the last part of our discussion on bonding in covalent compounds. And this is going to be another bonding theory that we are going to cover today. The title of the lecture is MO theory, which is molecular orbital theory is what it's called. It's not pronounced MO theory, it's pronounced MO. But let's talk about first why we even need another one. So we talked last time about valence bond theory, which is the key aspect of that is hybridization, where the atomic orbitals mix on the center atom, and then that leads to the formation of sigma bonds through the hybrid orbitals, and then if you have unhybridized p orbitals, you can form pi bonds. And that seemed like complicated enough and a pretty satisfying theory, so why do we need another one? Well, just like things we talked about earlier in the course, some of the theories just don't quite represent physical reality, or they have limitations to them, and valence bond theory is one of them. So one of the nice things about valence bond theory is that you can predict things about the bonding just based on the Lewis structure. As we always said, you start with the Lewis structure, and then based on the number of electron groups and the number of double bonds, you can predict the hybridization, you can predict how many sigma and pi bonds there are. All that stuff comes nicely from the Lewis structure. That's what's good about it, but sometimes it doesn't work. So let's draw the Lewis structure of a simple molecule O2, dioxygen or just oxygen. So what you would do is, oxygen has 6 valence electrons each, so you're going to need 12 valence electrons. and we're going to want to complete the octets. And so what you would find is you'd get something like this. You have to draw a double bond between the two to be able to complete their octets. Otherwise, you'd have at least one of the oxygen atoms that has an incomplete octet, and you would predict that you have 1 sigma and 1 pi bond based on what we learned last time. A double bond is always 1 sigma bond and 1 pi bond. Okay, so that's easy enough. Now, one thing that we haven't talked about yet in this course are what's the importance of how many unpaired electrons are. So we talked about unpaired electrons in the context of atoms, how we can take the electronic configuration, predict how many unpaired electrons are. Now, why is that important? Well, first, how many unpaired electrons would you predict from oxygen? Well, based on the Lewis structure, we always pair up the electrons and make bonds which have a pair of electrons in each, or lone pairs. So we would predict that there's 0 unpaired electrons in O2 based on its Lewis structure. Now, why does it matter how many unpaired or paired electrons there are? Well, that's because it determines what are called the magnetic properties of a substance. We haven't talked about this yet, but there's really 2 limiting magnetic properties that you can have, diamagnetic and paramagnetic. And when you have 0 unpaired electrons, you would predict that it's called diamagnetic, which I have to spell correctly first. But diamagnetic is what you predict anytime you have 0 unpaired electrons. And in terms of what that means in its magnetic behavior, that means it would be weakly repelled by a magnetic field. In reality, there's very little interaction with the magnetic field. It's not very noticeable. So that's what we predict for oxygen. Okay, we draw the Lewis structure, it has 0 unpaired electrons, it's going to be diamagnetic, it's going to have no interaction with the magnetic field, or just be very weakly repelled, if anything. Okay, that's what we predict, but let's go to a video that shows us what actually happens with oxygen. So what this video is going to have, I'm going to have the sound off, so I'll narrate it myself. So proper safety equipment first and foremost, so kudos to them. But they're going to take two liquids. So oxygen and nitrogen are normally gases in the atmosphere, as you guys all know. But if you cool them down enough, they form liquids. I think it's 77 Kelvin for liquid nitrogen, and probably just a little bit warmer. So it's really cold, bottom line. But you can make liquids out of them. And then what they're going to do is they're going to pour those liquids through a strong magnetic field, which is just, in their case, just 2 strong magnets next to each other. And they're going to see then how does that liquid interact with the magnetic field. That's what they're looking at here. So they're going to start with oxygen. And I'm not going to read what he's saying. I didn't realize I captioned it. So when he pours the liquid oxygen through the magnetic field, if it was diamagnetic, it should go right through, but you can see that it sticks there. It's actually attracted to the magnetic field. This is liquid oxygen we're looking at. Okay, so you can add more. It evaporates eventually because it boils at such a low temperature, but it stays there in the magnetic field while it's a liquid. It's strongly attracted to the magnets, which is not what you'd expect if it was actually diamagnetic. So that's what we actually see for oxygen. So it turns out that oxygen is what we would call paramagnetic, which means it has unpaired electrons and that it actually interacts with magnetic field. Now, I believe what they're going to do now, after an awkward pause, no, maybe they're not. Or did she jump no, they jumped the gun. Okay, they're not actually stopping now. That's what I thought. Okay, I haven't watched this in a while. They're going to do nitrogen now. So nitrogen is another liquid that, another gas. So that's oxygen. There, she did nitrogen, and it goes right through. Okay, so oxygen sticks like that. And then she has nitrogen, or did at one point. Oh, she's going to do it again. But the nitrogen, this guy just keeps doing oxygen. But anyway, if you watch it quickly, the one time they did it, the nitrogen went right through. So nitrogen is diamagnetic. That's how a diamagnetic substance behaves. It goes right through the magnetic field, but a paramagnetic substance would stick to it. So the whole point of this video was to show that in reality, the physical reality is that oxygen is paramagnetic. So that's what the observation tells us. So that means that the valence bond theory, which we would use to predict otherwise, is not correct. And again, paramagnetic means it has 1 or more unpaired electrons, and that is attracted to a magnetic field. So that can only happen if you have 1 or more unpaired electrons. All right, so we would never predict that by just drawing a Lewis structure. So we have to figure out, okay, what's a better bonding theory that accounts for that? Now, the reality is this better bonding theory is sort of the gold standard of bonding theories. It does the best job of describing the physical reality of how atoms bond to each other, but of course, like most things that are realistic, it's exceptionally complicated. So we're only going to talk about it for very simple diatomic molecules like O2, which are reasonable enough to deal with. It's not going to be too complicated for those. If you want to do anything more complicated, like a trigonal planar or a tetrahedral molecule, molecular orbital theory all of a sudden becomes a lot more difficult to deal with. If you take the other course that I teach, which is a graduate level inorganic course, so most of you probably won't get there, then we'll talk about molecular orbital theory on a lot more complicated and interesting things. But for this course, we're just going to do it for diatomic molecules. 2 atoms bonded together, that's it. All right, so let's talk about then some of the rules or the concepts involving this new molecular orbital theory. So we kind of, it's not too different from valence bond theory, but there is a key difference that we need to make sure we appreciate. And so what happens with molecular orbital theory is that we have atomic orbitals on each atom, and again, for our purposes, it's just going to be 2 atoms bonded together. It's as complicated as we're going to get. So you have these atomic wave functions, the s orbitals, p orbitals that we're going to be dealing with. And what they're going to do is they're going to be mathematically combined. So remember that wave functions are mathematical functions, and so we're going to mathematically combine these functions, make combinations of them. And the type of combinations that are going to be, they're all linear combinations. So we're going to basically add and subtract the atomic wave functions to each other. And so what this forms are delocalized molecular orbitals. So this is kind of the key difference between molecular orbital theory and valence bond theory. We're not going to get into the math of it too much. We didn't really talk about the mathematical functions of wave functions. We kind of just abstractly referred to it. They're going to be added and subtracted, but the key point is that when you do that, you form what's called a delocalized molecular orbital. So we no longer have, for example, let's think about the simplest one, H2, that we're going to get into in a little bit. And what we talked about last time with H2 was that, okay, hydrogen has a 1s orbital, the other hydrogen has a 1s orbital, and those 2 orbitals overlap, and in that overlap region, that's where you have the bond. Now, what molecular orbitals theory says is that we actually mathematically combine those 2 1s orbitals, and it forms a new orbital that's delocalized over the entire molecule. It no longer belongs to this atom or that atom. It's a new orbital that actually belongs to the entire molecule. So that's the key aspect of molecular orbital theory, is that the orbitals are now delocalized over the entire molecule. They're not individual atomic orbitals anymore. Okay? So in terms of, which of these orbitals, which atomic wave functions can actually mix with each other, is it just everything mixing with everything, or are there some limitations? There are some limitations on it. So the first is that, only orbitals that are close in energy can mix. So, if you have usually that means they're going to be in the same subshell, or at least really close to each other in terms of their subshell. So if you have an atom that has 1s and 2s orbitals that are filled, the 1s and the 1s can mix, the 2s and the 2s can mix, but the 1s is not going to mix with the 2s because they're kind of far apart in energy. So usually it's things that are really close in energy that can mix. And then the other thing that we will also talk about in more detail later on is that they have to be sort of lined up in the right way. So we also, just like we did before, we have sigma bonds and pi bonds. And so only the orbitals that are lined up in the right way to make sigma bonds will mix with each other to make the sigma orbitals, and only the orbitals that are lined up the right way to make pi bonds will mix with each other to form pi orbitals. So there's limitations there as well, as we'll see. And the ones that we only care about, just like we do for most things, are the valence orbitals. So, the core orbitals in an atom, they're buried, they're close to the nucleus, they don't really extend out very far, so it's hard for them to mix with other orbitals. And even if they do, they're not really consequential to the bonding, because they're just all filled and way down in energy. So what we really care about, just like we did for valence bond theory, are just the valence orbitals. All right, so let's talk about then the types of orbitals that we can have, where we're going to, again, take wave functions and mathematically combine them, add them and subtract them to each other. So one way that we can do this is we can add the 2 wave functions together. So again, it's an orbital on one atom, an atomic orbital on another atom, and we mix them together, and we can do that by adding the 2 atomic orbital wave functions. So we use psi to abbreviate wave functions for this as well, Greek letter psi. But the bonding orbital is going to be an additive combination of two atomic orbitals, one from each atom. So when you add the two together, that gives you a bonding orbital. And so that creates an orbital that's delocalized over the entire molecule, but the greatest electron density for that orbital is going to be along the bond in between the two nuclei. So when you fill these bonding orbitals, you're increasing the bond strength between the two atoms, because this has electron density between the nuclei, and so if you put electrons in there, you're going to be holding the two nuclei together. So it's greater along the bond in between the nuclei. Now, when we mix two atomic orbitals together and make molecular orbitals, the energies of those molecular orbitals are also different than the atomic orbitals that we started with. So it changes the energy when you do this. And the bonding orbitals are going to be lower in energy than the atomic orbitals. So when you mix two atomic orbitals to make a bonding molecular orbital, it forms an orbital that's lower in energy than what you started with. All right, so that's bonding. Now, the exact opposite process, or the exact opposite type of mixing, is called antibonding. And so when we do this, we abbreviate it with a star. So any molecular orbital or wave function that has a star next to an asterisk is going to be indicating that it's antibonding. That's how we sort of note that. And all we're doing in this case is just subtracting the two wave functions. So we're doing an out-of-phase combination or a subtractive combination. So the additive combination is called in phase, the subtractive would be called out of phase. All right, so just so for completeness, this is called in phase when you add them together. All right, so that's an antibonding orbital. And so when you form a delocalized antibonding orbital, the electron density in that is going to be greater outside the regions of the two nuclei, or outside what's called the internuclear region. And so as we'll see, when you put electrons into these orbitals, you're actually weakening the bond. You're causing the two nuclei to actually be pushed apart when you put electron density in there. It's not holding the nuclei together, it's actually pulling them apart. So it's kind of a balancing act between these two. And then the energy of the antibonding orbitals is higher than the atomic orbitals. On some level, we have still conservation of energy. You have the average energies of the two atomic orbitals that you're mixing, which are usually at the same energy if it's the same atom, and then one of the molecular orbitals goes below that energy, one of them goes above it. So the total energy is still the same. It's just one goes down in energy, one goes up in energy when you mix together. All right, so that's kind of abstract, but that's essentially at a very basic level what we're doing mathematically. Now, what's also helpful to think about are the pictures and the shapes of these orbitals. So we're going to start with a very simple case of mixing 1s orbitals. So something like H2, where each atom has just a single 1s orbital available for bonding. And so what we have then is, just like we did in valence bond theory, we have this distinction between sigma and pi. A sigma bond is along the bond axis, pi bonds would be sort of side to side. So when you have 1s orbitals, just like we talked about last time, you can only make sigma bonds with those. So when you mix two 1s orbitals together, you're always going to form a sigma bond. So we'll label the orbital as sigma. And then we usually put little subscripts to tell you which atomic orbital it comes from. That's also often done. So sigma 1s, and that one would be the in-phase combination of two 1s orbitals. And so then what that looks like, remember last time we sort of showed this as, okay, when you form a sigma bond, you have two different 1s orbitals that overlap. When you form a delocalized molecular orbital, it doesn't look too different, but now it's just a single orbital that's delocalized over the entire molecule. So if you have the two nuclei there, your bonding sigma 1s orbital is going to look something like this. It's going to be delocalized over the entire molecule, but most of the electron density is in between where the two nuclei are. So you put electrons in there and it's sort of going to attract the two nuclei together, holding together in a bond. That's why we call it a bonding orbital. So this is our bonding orbital when you have the in-phase combination. Now when we do the out-of-phase combination, we call that sigma star. Star means antibonding, and that's going to be a subtractive combination of two 1s orbitals. And so what this looks like is the two orbitals kind of, or the two halves of the orbital kind of repel each other. So you get like a region outside the nucleus like that, you get a node in between, and then the other one is added out of phase. Remember that the way that we indicate opposite phase in orbitals is we shade it in, so it'll look something like this. So when you have a region of opposite phase, you change the shading. Unshaded and shaded means opposite phase, and you have a node that's in between them, a region of 0 electron density, and this is what your antibonding orbital looks like. All right, so when we mix two 1s orbitals in something like H2, we always get one bonding orbital and one antibonding orbital. In phase is bonding, out of phase is antibonding. Now, what's going to be more important for us than the pictures of these orbitals and the mathematical functions that kind of represent them is going to be the relative energies of the orbitals and how we decide where the electrons go to then be able to understand how the bonding works in these simple molecules. So the way that we would draw this is we start with two 1s orbitals, same energy because they're both 1s, especially if they're the same atom, that would be the case. And then, as we said, we're going to form a bonding combination, and that bonding combination is lower in energy. So the middle part of this diagram shows how the orbitals mix together to form molecular orbitals. So on the outsides of your atomic orbitals, your molecular orbitals are in the middle, and so that's going to be your sigma 1s bonding orbital, and then the antibonding orbital will be higher in energy by some amount, by the same amount ideally. So if I drew it, didn't do it perfectly, but it's close. And so that's going to go up by the same amount of energy, and that's your sigma star. All right, so again, these are your atomic orbitals on the outside. So when you're drawing a complete molecular orbital diagram, it would usually show the atomic orbitals that are mixing together, as well as in the middle, the molecular orbitals that form by mixing those two together. In reality, the part that's most important for you to know and be able to internalize is the ordering of the molecular orbitals that are in the middle of the diagram, because that's going to determine what order we put the electrons in, and then we can make some predictions from there about bonding, magnetic properties, and so on. All right? And so for 1s orbitals, it's very simple because you have two 1s orbitals and they mix to form two molecular orbitals, sigma, which is lower in energy, sigma star, which is higher in energy. That would be true for any s orbitals, 1s, 2s, 3s, whatever you're mixing together. If they're s orbitals, this is how it works. And so as a general rule then, which plays out here in a very simple way with only two orbitals, the number of atomic orbitals that you're mixing or combining, which in this case is 2, equals the number of molecular orbitals formed. All right, so here we have two atomic orbitals and we form two molecular orbitals. And the most important thing for you to know is that the bonding molecular orbital comes first, then anti-bonding, okay? So that's what the diagram looks like. And now then, as we said, what we're going to be doing is we're going to be populating these with the number of electrons that that molecule has and figuring out how many electrons go into bonding orbitals, how many go into anti-bonding orbitals. And so what are some things then that we can predict from that? So there's really three things that we can predict once we have a molecular orbital diagram and once we put the correct number of electrons into it. So the first is going to be the bond order. We talked about bond order already, single bond, double bond, triple bond. We can predict that from the Lewis structure, but it's not always correct. But with the molecular orbital diagram, we can also predict it. And the way that we do that is a simple mathematical relationship. So it's going to be 1/2 times the number of bonding electrons. So that's going to be the number of electrons that are in bonding orbitals minus the number of antibonding electrons. All right, so as we said, when you put electrons into a bonding orbital, you strengthen the bond, meaning you increase the bond order. When you put electrons in antibonding orbitals, you weaken the bond, meaning you decrease the bond order. So it's sort of a competition between those two. The difference of those two multiplied by 1/2 gives you what the bond order would be. And then we can also predict the types of bonds that we have, which just like we saw in valence bond theory, they're going to be sigma, pi, or some combination. And I don't know if we'll see an example like this today, and this is not going to be a point we emphasize a lot, but one of the key parts about valence bond theory that we talked about last time was if you have a double bond, just like we talked about with oxygen, it's always one sigma and one pi bond, but we will, and if you have a single bond, it's always a sigma bond. But then with molecular orbital theory, you sometimes make some weird predictions like, oh, this molecule has a single bond, but it's actually a pi bond, not a sigma. Or this molecule has a double bond, but both bonds are pi bonds. There is no sigma bond. So it makes some predictions about the types of bonds that form that you would not get from, again, a simple valence bond theory approach. And you can use the diagram to help you predict that. So, but that's probably the least important of the three. The most important is going to be bond order and then also magnetic properties, which we kind of already introduced earlier. So based on how many unpaired electrons there are, you can predict whether it's diamagnetic or paramagnetic. So diamagnetic, as we said, means no unpaired electrons. And the physical behavior that results is that it's going to be weakly repelled by a magnetic field. And then paramagnetic means you have one or more unpaired electrons. And when you have that, it's going to be attracted to a magnetic field, just like we saw for liquid oxygen in the video. All right, so those are some other predictions you can make. As a little bit of a shortcut approach, we will occasionally do molecular orbital diagrams for either molecules or ions that have an odd number of electrons. If you have an odd number of electrons, it has to be paramagnetic. There's no way that they can all be paired. That's just arithmetic. But if it has an even number of electrons, as we'll see, it could be diamagnetic or paramagnetic, and you have to use the diagram to help you decide which of those it would be. All right, so those are some predictions we can make, and I want to cover those first, because now when we start putting in electrons into this first orbital diagram that we discussed, we can start making predictions about bond order and magnetism. All right, so here we're going to do it for a bunch of diatomic molecules that only involve mixing the 1s orbitals. So as we just introduced, when you mix two 1s orbitals together, so hydrogen only has 1s valence orbitals, it's the simplest atom in the periodic table. So when you mix the two 1s orbitals together, you get sigma and sigma star. All right, and that's what you're always going to get when you mix together s orbitals, whether it's 1s, 2s, and so on. So that's what we get, and then when we have these diagrams, we know how many valence electrons there are, we can start putting those electrons into these orbitals. So for H2+, it's only one electron, because hydrogen has one electron each, but you take one out for the positive charge, it leaves you with only one. And when we're filling these molecular orbital diagrams, we follow the same rules that we did for atomic orbitals. We fill lowest energy to highest energy. So whenever we're populating these orbitals with electrons, we go to the lowest energy one first. We put up to 2 electrons per orbital before we move up and start filling the higher ones. So for this one, the single electron that we have has to go down here to give us the ground state configuration. All right, and so the bond order for this H2+, this dihydrogen cation, remember that the way we calculate that is 1/2, and then we take the number of bonding electrons. We have one electron that's in a bonding orbital, that's sigma 1s, minus the number of antibonding electrons. Sigma star is empty, so there's 0 antibonding electrons in this diagram. And so that gives us a bond order of 1/2. So the other thing that we can predict using molecular orbital theory are bond orders that are fractional, that don't have to be 1, 2, or 3, but can be 1/2, 1.5, 2.5, somewhere in between there, which we would never have gotten from a Lewis structure. Try to draw a Lewis structure that has a half bond order, and you're going to struggle mightily. So this gives us that information in a pretty straightforward way. Now let's go to H2, the neutral, dihydrogen, and we would predict from valence bond theory that this is just a simple, single bond like that. Let's see if the molecular orbital theory jives with that. So we're going to have the same valence orbitals available, 1s on each hydrogen atom, forming a sigma and a sigma star when they mix together. And then what we'll do is we'll populate this with now 2 electrons. Neutral dihydrogen has 2 electrons, 1 from each hydrogen atom, is a total of 2. And just like before, we start with the lowest energy orbitals. Each orbital can get up to 2 electrons, so both of them we're going to go into sigma 1s this time. All right, we always fill lowest energy to highest energy orbitals, 2 electrons maximum per orbital. So calculating the bond order of this, we get 1/2. This time we need the number of bonding electrons. Well, now we have 2 electrons in the sigma 1s orbital, so that's going to be a 2, and we're going to subtract the number of electrons that are in sigma star, the antibonding orbital, which is still 0. So for this, we get a bond order of 1. So molecular orbital theory predicts that it's a sigma bond, single bond, both electrons paired, exactly what we would predict just from drawing the Lewis structure. So it's not always that the molecular orbital diagram and the Lewis structure don't match with each other. In many cases they do. So this is an example where everything we would predict from a Lewis structure, a single sigma bond with no unpaired electrons, that's exactly played out in the orbital diagram as well. All right, and we can keep going. We can do this with other ions as well. So if we have H2 minus, or this would be the same diagram as the dihelium cation, they both have the same number of electrons, which is 3 in this case. So now when we have 3 electrons, it's again for H2 minus, 1 from each hydrogen atom plus 1 more from the negative charge, same valence orbitals. And then now we have 3 electrons to put in though. And so when we have 3 electrons, the first 2 go down here, but we can only put 2 electrons per orbital, so we have to put 1 up here in the antibonding orbital. So now what we've done is we've taken 1 more electron up in the antibonding orbital, so let's see how that influences the bond order. So this time when we calculate the bond order, we still have 2 electrons in the bonding orbital, but now we have 1 that's up here in the antibonding orbital. So it's going to be 1/2 times 2 minus 1, which gives us 1/2 again. So this molecule also has a 1/2 bond order, this time because we had to put 1 electron into sigma star. That weakens the bond, makes the bond order a little bit smaller from 1 to 1/2. And then finally, if we get to helium, now one thing we've talked a little bit about with noble gases, helium is the first noble gas, is that, well, they don't usually make bonds with anything else. And we saw some rare exceptions with like xenon fluoride compounds. But in general, we say, okay, noble gases don't make bonds with each other. So does helium-2 actually exist? So let's use an orbital diagram to predict that. So for helium-2, we're having the same orbital diagram. Draw it over and over again. Sigma and sigma star, 1s. And then this time we have 4 electrons. Each helium has 2 valence electrons, total of 4 for the whole molecule. So when we populate the diagram this time, we have to fill both orbitals. 2 electrons per orbital is all we can do. So when we calculate the bond order of this 1/2, the number of bonding electrons is 2, but the number of antibonding electrons is also 2, because we had to put 2 electrons up there as well. 2 minus 2 is 0. So what does it mean when we predict a bond order of 0? Well, bond order of 0 means there is no bond. It's essentially what that's telling us. So it tells us that the molecule is unstable and doesn't exist. So whenever you calculate a bond order of 0, it essentially tells you that the bond and the antibond cancel each other out, and there is no actual bond between those 2 atoms. So dihelium is an unstable molecule. It wouldn't exist, and that's what we would also predict for noble gases based on what we already know, that noble gases don't tend to bond to each other, and this is why, because if they try to bond to each other, you fill the bonding and the antibonding orbitals, and they fall apart. All right, so any questions so far on the s orbital diagrams, the simpler of the ones that we'll do? Yeah?
So when it's a half or a fraction, what is that?
I mean, the half bond order would be, this bond would be weaker than a single bond, than a bond order of 1, but it's not that it doesn't exist or that it's completely unstable. So it's a weak bond, but it still exists as long as it's non-zero. Anything else? Okay. But let's talk about what happens with p orbitals, because we also are going to do molecular orbital diagrams for diatomic p block atoms as well, so carbon, nitrogen, oxygen, and so on, those things on the right hand of the periodic table. So when we have p orbitals, there's 2 ways that they can mix together. So when we mix together 2 p orbitals, they can either come head-to-head and make a sigma bond, or they can come side-to-side and make a pi bond. We kind of already talked about that in the context of valence bond theory. So the same thing happens with molecular orbitals. When we mix together 2 p atomic orbitals to make molecular orbitals from them, they can either make sigma or pi molecular orbitals. So the sigma ones, we're going to assume, I hate that this is the way that general chemistry books do it, because it's not actually the standard that we use in chemistry, but I'll try to be consistent with what the book has, I believe, unless they've changed it. We're going to assume that the bond axis is the x direction. So basically, along the bond, horizontal is x. I guess makes intuitive sense. Okay, so what we have then is, if we mix together 2, remember in the p orbitals we have px, py, and pz that face in the different directions. So if we mix together the 2 px orbitals, those are going to be the ones that are facing each other right along the bond, if we say that the bond is the x-axis. So if we make a sigma p molecular orbital by doing an in-phase combination of two px orbitals, and so what in-phase combination means is that we're going to have, I'll do the nucleus in a different color here so you can see it more clearly. We have one p orbital. It's going to have a figure 8 shape. Let me draw it correctly. So that's one p orbital, and again, one of the lobes is opposite in sign to the other, which is fairly important for what we're talking about here. So this is a px orbital. And we're going to do an additive combination with another px orbital. Now, an additive combination means that we want the two phases that are the same to line up. So if we're going to draw this phase as unshaded or white, we're going to have the other one that's white facing that in the same direction, pointing towards it. So we want those two to be able to mix together. So you get px plus px, where the two like phases mix with each other in that direction. And then what that forms is a sigma orbital, which would be from the two, sigma p orbital, where you have nucleus and nucleus. You have a lot of electron density in between the two, where those two unshaded lobes sort of mixed with each other. And then you also have the opposite phase sort of outside of there. That comes from these other lobes that are present. But the majority electron density is in between the two nuclei, so it'd still be classified as a sigma bonding molecular orbital. So that's the in-phase combination of two px orbitals that are pointing right at each other. We also have the out-of-phase as well. So a sigma star orbital would be an out-of-phase combination between those two, where we take those same two p orbitals, or now we're going to subtract them. And so what it means when we subtract two orbitals, as we kind of talked about with s orbitals, is that you're going to take one of them and sort of flip the sign, basically flip the whole thing over. So now what you're going to have is the unshaded lobe from this orbital is going to line up with the shaded lobe from that when we flip the sign of it. And so what you again get is a node in between the two nuclei. So this one's a little bit more complicated to draw. And as I said, the shapes of these is not really the important part, but I just want to get an idea what they look like. So the unshaded and shaded parts sort of overlap with each other and destructively interfere to give the node in between, and then you have the opposite phase, so on the outside. So the majority of the electron density is again outside of where the nuclei are, and it's an anti-bonding orbital, sigma star. All right. So the p orbitals that are aligned along the direction of the bond, in this case what we call the x-axis, just like s orbitals, they overlap head-to-head and they form a sigma bonding orbital that's lower in energy and a sigma star that's higher in energy. So that's one thing that p orbitals can do. But there's also the possibility of forming pi bonds as well with p orbitals. And so what you have in this case is if the two p orbitals that you're mixing are sort of side to side with each other, they're going to form delocalized pi molecular orbitals. So one of those would be, if we call y the vertical direction, so we said that this was x along the bond, we'll call this y. So if we take our two py orbitals and mix them in phase, what that's going to look like is we're going to have two p orbitals that are lined up like this. And so with the in-phase combination, we're going to take these same phases and sort of overlap them with each other and delocalize them in phase. And so what that gives us is a molecular orbital where you have nucleus and nucleus, and now the electron density is greatest above and below where that bond would be. So it's going to have a shape kind of like this. You have a in-phase lobe that's above the bond, an opposite phase lobe that's below the bond. But again, the key point is that it's a single delocalized orbital over the whole molecule. It's no longer two separate p orbitals. It's what's now called a pi molecular orbital. Bonding orbital. So that would be your bonding combination where they're in phase. And then we have the out of phase pi star antibonding, which is going to be taking those same two orbitals and subtracting them from each other. So if we have these two p orbitals, now we do an out of phase combination, py minus py. What you end up with is a situation where when we do them out of phase, that means we're flipping one of the orbitals and we're having the unlike phases now lined up with each other, so they're going to destructively interfere. So that's going to be your bond axis, and then you're going to have electron density outside of that, like this, where again it's the unlike phases that are lining up with each other, and so there's destructive overlap, no constructive overlap, and you get a node in between, just like we did for the other antibonding orbitals. So this is your pi star. All right, so when we have p orbitals that are aligned perpendicular to the bond axis and they come together side to side, they can make pi and pi star, pi bonding and pi antibonding orbitals in that way as well. So I'm not going to draw the other one, but the same thing happens with pz. So we have px, py, and pz. Pz is also perpendicular to the bond, although in the coordinate system that I've defined, those will be the orbitals that like point straight out at you guys, so it'd be a little bit hard to draw in the same orientation. But the same thing happens with pz, just rotated 90 degrees. So imagine you take these two orbitals and just rotate them towards you. That's what the pz ones look like. And so that gives, so what ends up happening then is that because you have the same thing happening for py and pz, the pi orbitals and the pi star orbitals that form from those are degenerate. So for each pi orbital, you actually get two orbitals that are at the same energy, one in the y direction, one in the z direction. So you get what are called degenerate orbitals. Remember, degenerate means at the same energy. So that gives you two degenerate pi bonding orbitals and two degenerate pi antibonding orbitals whenever you mix together a set of p orbitals. All right, so in summary then, and we'll see this more clearly on the diagram on the next page, when you have a set of three p orbitals mixing together, three from each atom, remember that each set of p orbitals is px, py, and pz, one pair of those orbitals, which we called px, mixes head-to-head to make sigma and sigma star. The other two pairs mix side to side to make pi and pi star, and each pi orbital is two degenerate orbitals, or not each pi orbital, each pi level is two degenerate orbitals, one in the y, one in the z direction. Each pi star is also two degenerate. So you get those possible, it's more complicated obviously with p orbitals. But let's then look at what this looks like. So we're going to do an orbital diagram. Now the other complication with the p block elements is that the ordering of the orbitals changes a little bit depending on which part of the periodic table you're in. So that's the other little complication we have to deal with. So we'll start with actually the second half of the p block, O2, F2, and neon 2, the p, this is P4, P5, P6 for the atomic configuration. And we'll see the order for those because that's the more intuitive one. Okay, so what we have here for oxygen is that the valence orbitals are 2s and 2p. So we have mixing of both 2s and 2p orbitals in O2 or any of the other p block elements. And then in terms of the molecular orbitals that result, just like we saw for s orbitals before, the 2s orbitals mix to make sigma and sigma star. So that's the easy part of the diagram for us. And then as we just finished talking about, the 2p orbitals can mix in two different ways. They can form either sigma or pi molecular orbitals. Now, the thing we haven't talked about yet with sigma and pi is what's the relative energies of them. So another part of molecular orbital theory that we haven't really described yet is that how strong the overlap is between the two orbitals is going to dictate how much energy decrease you have for the bonding orbital and how much the antibonding orbital increases. Basically, the spread of those two orbital energies depends on how strong the overlap is. So it's not too hard, I think, to visualize. If you have a sigma overlap where the two orbitals are head-to-head right at each other, that's going to be a stronger overlap than you have two orbitals side to side. So because of that, because the sigma overlap is stronger, the sigma 2p orbital goes lower in energy, and the sigma star 2p goes higher in energy. All right, and that's why those two sort of spread out further, because the head-to-head direct sigma overlap is stronger than the side-to-side pi overlap. And then at the pi levels, again, you have two degenerate orbitals at each level. The ones that are low in energy are the pi bonding orbitals. There's two of them, one from the z direction, one from the y direction, and then you have the anti-bonding, where there's also two of them up there. And again, the number of orbitals that we mix together has to equal the number of molecular orbitals. So we mix together 6 2p orbitals, and we get 6 molecular orbitals that arrange in this way. So again, the most important part of the diagram for you guys to remember is sort of this middle part here, the order that these molecular orbitals come in. However you choose to internalize that is fine with me, but that's what you have to sort of remember. So there's some things I guess we could add to the diagram. So again, the outside parts of the diagram represent each oxygen atom before they're mixed together. And then in the middle we have O2 when the two are bonded. Okay, and now we have to put in the correct number of electrons. So oxygen is 6 valence electrons, it's group 6, so O2 would have a total of 12, 6 from each oxygen atom. So we're going to populate this diagram with 12 electrons, and think back to what we did at the very beginning. I would say we predicted that O2 would be paramagnetic. Let's see if the diagram gives us that. Okay, so when we have 12 electrons, we go lowest energy to highest energy, so we put 2 there, and then 2 there. That's 4, that's 6. Now we get up here to the pi. Remember that when we have degenerate orbitals, we're still going to follow Hund's rule. So we're going to go 1 and then 1, and then we're going to pair them up. But those all get filled anyway. So that's a total of 10, 2, 4, 6, 8, 10. So now we have 2 more out of our 12 to put up here. And to follow Hund's rule, we put 1 into each orbital, and we do them with the same spin. So Hund's rule still applies to molecular orbitals as well. When we have degenerate orbitals, we fill them singly first with the same spin before we pair them up. And so what we find then is that because these 2 electrons up here are unpaired, we would predict that O2 is paramagnetic. So this bonding theory does give a prediction that matches what we would observe experimentally. So this was one of the crowning achievements of molecular orbital theory, the fact that it correctly predicted the magnetism of things like O2, which a Lewis structure and valence bond theory would not be able to accurately predict. All right, so that deserves an exclamation point, so that's pretty cool. So we again put the 12 electrons in, and the last 2 that we put in are unpaired, which is where we get the prediction of paramagnetism. We also predicted earlier that O2 would have a double bond. We needed to put the double bond there to complete the octet. So let's see if that is true from the orbital diagram. Okay, so let's do the bond order for this. A little bit more complicated because you have more electrons, but still the same relationship. We say we take 1/2. We start with the number of bonding electrons. Those are the electrons that are in the orbitals that don't have stars next to them that are bonding. So we have 2, 4, 6, 8. So all the bonding orbitals are filled with 8 total electrons. Then we have to subtract the number of electrons that are in antibonding orbitals. So these 2 in sigma star are antibonding, and then these 2 up here in pi star are also antibonding. So there's a total of 4 electrons that are in antibonding orbitals that have a star next to them. So that's going to be a 4. And so 1/2 times 8 minus 4 is 2. So again, we predict a double bond from the Lewis structure, and that still matches what we get from the molecular orbital diagram. So we get a double bond for this one. So whenever you're subtracting these 2 numbers here to calculate the bond order, the 2 numbers that you're subtracting add up to give you the total number of electrons. It's just how many of them are in bonding orbitals, how many are in antibonding orbitals, and then subtract those 2 from each other and multiply by 1/2. All right, so any questions on that so far? Now, the other thing that you can do from an orbital diagram, which will kind of be how some of the homework questions are set up, is write an electron configuration. So we have atomic electron configurations, which are covered on the exam this week. 1s2, 2s2, whatever. And we can do the same thing for molecular orbital configurations. So we just write out each orbital level and how many electrons are in it. So for O2, what you would get is sigma 2s has 2 electrons. Usually we just write them in the order that they come in the diagram. Sigma star 2s has 2 electrons. Sigma 2p has 2. Pi 2p has 4. We usually just group those together into basically one energy level, just like we do for a subshell. And then our pi star 2p has 2 electrons in it. So that's how we would write the configuration for this molecule, which is what we might have you do in some of the homework questions is in a multiple choice question, pick out the correct configuration. So this doesn't give us as much information because it doesn't tell us how many electrons are unpaired, but we could still use this to predict the bond order and then things like that. So for magnetism, we do need to draw out the diagram and figure out. And for these types of diagrams, you really only have 3 possibilities. It's either diamagnetic, which means all the electrons are paired. If it's odd number of electrons, it has to be paramagnetic with 1 unpaired electron. And It could also be paramagnetic with 2 unpaired electrons, so that's where you have to actually draw the diagram. But those are really the only 3 options you have. All right, so any questions on this one? So, you know, the 2p elements are more complicated, but it's still the same concepts that we've been covering so far today. Now, the other tricky part about the 2p elements, let's go on and let's do the other ones in the second half first. We haven't gotten to the tricky part yet. So let's just do it for fluorine, F2. So this is going to be the same exact diagram as O2, just different number of electrons. So when we draw the diagram for fluorine, we're going to just repeat what we did. We have 2s and 2p valence orbitals on fluorine. The 2s orbitals mix to make sigma and sigma star. So that sigma's at the bottom, not sigma star. And then the 2p orbitals mix to form sigma or pi. So you have a sigma 2p and then a pi in that order. And then you have your pi star and sigma star. All right, so same exact orbital diagram. Again, it's going to be key for you to remember, at least the middle part of the diagram, what order they come in. I guess one thing I didn't do in the last diagram, which you don't have to do, but for completeness you could, is you can also indicate the atomic configuration of each of these. So oxygen is 2p4. You don't have to put those electrons in. Again, it's just the middle part that we care about. But if you wanted to show the atomic configuration on the outside and then the molecular configuration on the inside, that would be a more complete way to do it. So for F2, each fluorine atom, which is on the outside, is 2s2, 2p5 valence configuration. So this would be what they would each look like. But then what we really care about is how the electrons arrange themselves here in the middle of the diagram. So each fluorine has 7 valence electrons. It's in group 7, 2s2, 2p5 as we just drew. So you're gonna have a total of 14. Okay, so we're gonna dump 14 electrons into the middle of this diagram here, and so we go 2, 4, 6, 8, 10, 12, 14. This time they're all paired, so we have no unpaired electrons anymore. So we would predict this is diamagnetic, which is true. F2 is kind of dangerous stuff. You don't want to dump it through a magnetic field like we did with oxygen and nitrogen, but if you were brave enough to do that, well, you'd probably corrode the metal, but that's a different story. So anyway, if you're brave enough to do that, it would be diamagnetic, it would go right through, and that's true. We can predict the bond order for this. If we drew the Lewis structure of F2, we would predict a single bond. Let's see if that's also true from the molecular orbital diagram. So if we calculate the bond order for this, what you get is we still have 8 bonding electrons. All 4 of our bonding orbitals are filled. Sigma 2s, sigma 2p, pi 2p are all filled with a total of 8 electrons. And then for the number of antibonding electrons that we now have, we have 2 more electrons. They both went into antibonding orbitals. So we have these 2, and then we have 4 up here. Pi star is completely filled, so a total of 6 antibonding orbitals, or electrons, sorry. And that gives us a bond order of 1. All right, so this one we have really no different prediction than we would get from the Lewis structure. It's diamagnetic and has a single bond. This is exactly what the Lewis structure would predict, so this is one of those where there really is no conflict. I would say, in general, I can't think of an exception to this, the bond order is going to be consistent between the Lewis structure and the molecular orbital diagram. The difference is that for molecular orbital diagrams allows you to predict bond orders for weird things where it would not be easy to draw a Lewis structure, like odd electron things, or even some diatomic molecules where like you couldn't even complete the octet. How would I draw a Lewis structure of this? If you put the electrons into the orbital diagram, you can predict the bond order, whether or not you can draw a good Lewis structure. But in cases where the Lewis structure is straightforward, like O2 and F2, or nitrogen N2, the bond order that you predict from the orbital diagram would be the same that you get if you drew the Lewis structure correctly. But the molecular orbital diagram is a little bit more powerful because it gives you more information and allows you to make bond order predictions for things where a Lewis structure would not be easy to draw. So that's kind of the difference. All right, and then this one would be a configuration of sigma 2s2, sigma star 2s2, so 2 electrons in each of those. Our sigma 2p is filled, pi 2p is filled with 4 electrons, and then our pi star now has 4 electrons as well. All right, so that's going to be the electron configuration for F2, the molecular orbital configuration. right, so that one's just a pretty trivial extension, yeah?
How did you draw the electrons on the outside? What did you?
In reality, you don't have to do that. That's just for completeness. So what the outside part of the diagram shows you is each individual fluorine atom before they mix together and form a bond. And so each fluorine atom is 2s2, 2p5 for its valence configuration. That's what you get from the periodic table. So that's what each fluorine atom has. And then when you mix them together, what we really care about is how the electrons then redistribute once the molecular orbitals are formed. Yeah. Anything else? All right. And then the last one we'll do is neon 2, Ne2. Now, we already talked about noble gases with helium. We said, well, noble gases don't tend to form bonds with each other. So, for helium, we predicted a bond order of 0. Does the same thing happen with neon? So we have same orbitals. I'll do this one a little bit more quickly. 2s and 2p. I'm not going to put all the electrons in the outside this time. Hope you'll bear with me for that. Again, that's just window dressing. I don't really need that too much. And then you have sigma, pi. I'll put these to the side a little bit because it makes it less crowded. Pi star and sigma star. So same ordering of orbitals. This time we have 16 valence electrons, group 8 element, and then 2 of them bonded together, or trying to bond together. So we put 16, we get 2, 4, 6, 8, 10, 12, 14, 16. So we filled up the diagram completely. Every orbital is filled. And so when we calculate a bond order for that, just like we did for helium, all the bonding orbitals are filled and all the antibonding orbitals are filled. So we have 8 bonding electrons. Half of our 16 are in bonding orbitals, 2, 4, 6, 8. And then the other 8 are antibonding. These 2 from sigma star, these 4 from pi star, these 2 from the other sigma star. So 8 minus 8 is 0. So just like we got for neon, we would predict that there is no bond for helium. We predict there's no bond for neon, and this is an unstable molecule. So helium and neon, both noble gases, don't form bonds that are in diatomic molecules, as we would predict. All right, so that's the last one, but that one's kind of a trivial one because it doesn't even exist. We can't even write a configuration for it because it's not a molecule that actually exists. All right, so that was the slightly more, I think, intuitive 2p orbital diagram because, again, in here we have that head-to-head overlap is stronger, which is why the sigma 2p went lower in energy than pi. But the other thing that can happen, this happens in the first half of the p block, so boron, carbon, and nitrogen, p1, p2, and p3 configurations. Those 2 bonding orbitals actually switch with each other. So I'm going to point that out as I draw this out. But it's still the same valence orbitals, 2s and 2p. And they still mix to form the same types of molecular orbitals, but the ordering is a little bit different for this first half of the p block. Now that's something that if we're just calculating the bond order, if we forget that, well, that's not going to affect our calculation. But for getting the number of unpaired electrons correct, or for predicting what types of bonds you have, whether it's sigma or pi, you need to remember that there's a little bit of a switch here. So for 2s, it's still the same, sigma and sigma star. That'll never change. But the one part of this diagram that's a little bit different is at the pi level here. So what happens is that in the 2p orbitals, we had sigma and pi bonding orbitals. Before the sigma was lower in energy and then pi, here it's the opposite. So the pi 2p comes first in this part of the periodic table. And then you still have pi star and sigma star in the same order. So that's the only thing that changes. I'm going to highlight that with a red box. This ordering here is what switches in the first half of the p block. So these 2 switch. And this is, again, not as intuitive because we would expect that the sigma orbital is a stronger overlap, so it should come lower in energy. But in here, it doesn't. I'll try to explain a little bit about why that is, although it's kind of complicated for an introduction to molecular orbital theory that you guys are getting today. So you may or may not follow my explanation, but I'll try. So again, in the first half of the p block, p1 through p3, those columns, boron, carbon, nitrogen, this ordering is what switches. Pi comes below sigma for these ones. Now, why is that? Again, the explanation is complicated, but basically, when you mix atomic orbitals to form molecular orbitals, it's not only that s orbitals can mix with s orbitals and p orbitals can mix with p orbitals. It's also true that any orbital that's sigma can mix with any other orbital that's sigma. And so what you get for these ones is the 2s that form sigma interactions, as well as the 2px, the one that's also in the sigma direction, those all kind of mix with each other. You get a more complicated situation where s and p are mixing with each other. And so then what that does is it drives up the energy of this one a little bit. And the reason it happens for these ones and not for oxygen, fluorine, and neon is because in the left half of the p block, the 2s and 2p orbitals are closer in energy. So in order for orbitals to mix, they not only have to be pointed in the same direction, but they also have to be close enough in energy. For these atoms here, 2s and 2p are close enough in energy, and those that are in the sigma direction can all mix with each other, and that perturbs the ordering. Again, that's not something you're going to be tested on. That's just why it happens. I don't want you to think that this is just totally random or that I don't understand why it happens, but you don't need to understand why it happens if you didn't follow what I just said. But the important part that it does. But anyway, once we recognize that that's the correct ordering, we can now just populate it with the electrons. So let's do it for diboron, B2, 6 valence electrons. And so what we get for that is 1, 2, 3, 4, 5, 6. So again, following Hund's rule, we fill those ones with each one electron. So we would predict that this molecule is paramagnetic. The bond order in this, we have 4 electrons in bonding orbitals. Sigma 2s, pi 2p each have 2 electrons each. That's 4 bonding electrons. And then we have 2 here in sigma star that are antibonding. So 1/2 times 4 minus 2, we predict that this is a single bond, a bond order of 1. And the configuration for this is sigma 2s2, sigma star 2s2, and then pi 2p2. All right, so that's our configuration. Now what's weird about this one though is it's a single bond order of 1, and from valence bond theory we would have said, okay, that's a sigma bond. All single bonds are sigma bonds, end of story. But actually what we see in this case is that the sigma and the sigma star cancel each other out, so the net bond in this is actually a pi bond. So it's a single bond, but it's actually a pi bond, not a sigma. So again, that's another weird prediction that we can make from molecular orbital theory that we would have not made with valence bond theory. So it's a single bond, but it's actually a pi bond, not a sigma. And that's again because that last orbital that's filled is pi, the sigma and the sigma star from 2s cancel each other out, and that leaves a net pi bond. And also, this is one where if you try to draw a Lewis structure for B2, you're going to be like scratching your head for hours and not getting anywhere. So this would be a hard one to draw a Lewis structure of and predict that or the bond order, but from the diagram we can easily get that the bond order is 1. It's a single bond. Once we have the diagram, once we have the right number of electrons in there. All right, so that's boron. Let's go to dicarbon. Again, something that doesn't actually exist or that you wouldn't be able to draw a Lewis structure of, but we can predict the bonding from this diagram. So it's the same diagram as the previous one. 2s and 2p valence orbitals mixing together to make sigma and sigma star for the 2s. Those are always the same. Here, because we're in the first half of the p block, pi 2p comes first, so you have to remember that. And then we have pi star and sigma star. Okay. So those are the orderings of the orbitals. And then for carbon, it's now 8 valence electrons. So we're just going to put 8 instead of 6 in, just like we did last time. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we fill both of our pi orbitals. So this one would be diamagnetic. Did I get the last one right? Yeah. So that one's paramagnetic, this one's diamagnetic. With a sigma 2s2, sigma star 2s2, pi 2p4 configurations. That's the number of electrons in each of those filled energy levels. And the bond order for this is we have 8 total electrons, and 6 of them are in bonding orbitals. These 2 down here, and then these 4 are all in bonding orbitals, orbitals that don't have stars next to them. So that's 6 in bonding orbitals. And then these 2 sigma star are anti-bonding. So 1/2 times 6 minus 2 is 2. So this is a double bond. But again, the prediction about the type of bond that it is diverts from what we would have gotten from valence bond theory. So in valence bond theory, if we had a double bond, we always said, okay, it's 1 sigma and 1 pi. Well, in this molecule here, is actually, there's no sigma bonds because sigma and sigma star cancel each other out, and so both bonds are actually pi bonds in this molecule. Again, this isn't like a stable common molecule. You don't see C2 floating around everywhere. But the prediction, at least, is that it's actually a double bond that's made up of 2 pi bonds, not a sigma and a pi. So there's some differences there, again, between this and valence bond theory in terms of the types of bonds that form as well. And this would be another one where drawing the Lewis structure is kind of difficult and not straightforward. Okay? All right, any questions on that? All right, and then the last one we'll do is nitrogen N2, which is, now we would predict from a Lewis structure. This one is pretty easy to draw a Lewis structure of. And that it's just a triply bonded diamagnetic molecule. So let's see if that's true from the microorbital diagram. And then this would be a sigma, pi, and a pi. So those are the predictions we would get from valence bond theory. Triple bond, sigma bond, 2 pi bonds, diamagnetic. Let's go in the microorbital diagram and see what comes out of this. So this one follows the same order as the last two. Valence orbitals are the same, and then when they mix, you get sigma and sigma star. And pi comes first, before pi star and sigma star. So again, in these bottom two 2p molecular orbitals, the ordering is what switches sometimes, and here it does for nitrogen as well, with pi coming below. This one has 10 electrons, so we go 2, 4, 6, 8, and then 10. So we filled up all these bonding orbitals. So we predict this diamagnetic, which the Lewis structure would have given us as well. The bond order for this, we said the Lewis structure gave us a triple bond. Let's see if the microorbital diagram does as well. So of our 10 electrons, 8 of them are in bonding orbitals. These two down here, 4, 6, 8. All those are in bonding orbitals. And then the only 2 that are antibonding are the sigma star. These 2 electrons are antibonding, so we subtract 2. And that gives us a bond order of 3. We'd also predict from like orbital that it's a triple bond. So this is one where there's really no conflict between the Lewis structure and the microorbital diagram. Bond order is the same, sigma and 2 pi bonds, just like we would predict. So it's one where there's really nothing new to come out of the orbital diagram. So any questions on those ones? Yep.
You said it has a 1 sigma, 2 pi bonds?
Yes. So the way that we can tell that is down here, the sigma and sigma star cancel out. So there's really no net bond from the 2s orbitals. But then up here we have 2 filled pi orbitals, so that's 2 pi bonds, and then 1 filled sigma orbitals, that's your 1 sigma bond. So that's how that works. All right. All right, the last thing we'll cover with this diagram, before we close up with something that's a little bit out in left field, but you'll have to bear with me on that, is fractional bond orders. So again, just like we saw with some other examples earlier, it is possible to get bond orders that are not whole numbers. So all the neutral diatomic molecules that we did, so we did all the way from B2 up to Ne2, the whole 2p block, we already drew those diagrams. Those are all whole number bond orders. 0 for neon, and then 1 for some of them, 2, and then triple bond for nitrogen as high as we got. But if you have an odd number of electrons, you will get fractional bond orders that are something 0.5. So let's see how we would do that. It's very similar to what we got before. So if we have the dinitrogen cation, so if we take N2 and we remove an electron from it, I think it's called a diazonium cation, but don't quote me on the name of it. But anyway, that would be 9 electrons now, because N2 by itself had 10 electrons. We take 1 off for the cations, that makes it 9. So let's see how that changes the orbital diagram. So it's still the same ordering of orbitals. When we have cations or anions, we don't make any different predictions about what order the orbitals come in. We just have, all it affects is the number of electrons that are in there. And so we still have sigma and sigma star 2s, and then pi 2p comes first, which for getting the bond order, again, that doesn't really matter, but for the number of unpaired electrons, it... And again, I want to help you guys sort of, figure out some shortcuts to answering some of these questions. Obviously, the faster you can answer a question, the better. So if we correctly determine that this has 9 electrons, it's an odd number, that means we already know before we start that it's going to have 1 unpaired electron. That's the only way you can do it in these diagrams if you have an odd number of electrons. It has to be 1 unpaired. So if the question was, how many unpaired electrons does the N2 cation have? Well, your answer will be 1. You don't even have to draw the diagrams. It's an odd number, it has to be. Now, if we ask you for the bond order, though, for that you do need to consider at least which orbitals are populated and calculate the bond order like we've been doing. And so for this one with 9 electrons, we're going to still fill bottom to top. So we go 2, 4, 6, 8, and then just 1 up here in sigma 2p. So when we calculate the bond order for this, I won't write out the whole configuration again, but the bond order we have, out of our 9 electrons now, 7 of them are in bonding orbitals. Those 2, those 4, plus the last one. All 7 of those are in bonding orbitals, and then it's still these 2 sigma star. So it's 1/2 times 7 minus 2, which is 2.5. So basically when we compare nitrogen to N2+, we've removed 1 electron from a bonding orbital, and so that decreases the bond order by 1/2, from 3 for nitrogen to 2.5 for this. So we can again predict fractional bond orders, and that's going to happen anytime you have an odd number of electrons, okay? All right, any questions? The last thing that we're going to cover, which I think your book takes like a little bit of a leap of faith in covering this, but I'm going to go through it just because your book does, even though it's a little bit complicated, and I should be able to get through most of this, is the other thing that molecular orbital theory allows us to do, although it's fairly complicated in bigger molecules, so we don't really cover the details of it, is we can talk about delocalization over larger molecules, over more than 2 atoms, but entire structures. So let's consider this organic molecule called benzene, C6H6. All right, so C6H6 forms a hexagon of carbon atoms. You guys are going to learn all about this if you take organic chemistry. So this is just a preview. So it's a hexagon of carbon atoms. Each carbon atom has a hydrogen on it outside the ring. And then we have alternating double and single bonds. So double bond, double bond, double bond. Now, as you might recognize from our discussion of resonance in chapter 3, we could have also put alternating double bonds in the opposite position. So instead of here, here, and here, they could have been starting here. So there's 2 resonance forms of benzene, where it's still the same hexagonal shape, but then we move the double bonds to the opposite positions, the alternate positions, I should say. All right, so the double bond could have been here, here, and here. So these are exactly the same alternating single and double bonds, but just 2 different possible ways of drawing it. Those represent the 2 resonance forms. And the way that this is sometimes drawn then to indicate that is that ran out of room again, but this is good enough. Just to give you an idea, what it really means is not that we have alternating single double bonds, but that these pi bonds, we have 3 pi bonds in the structure, here, here, and here. Those pi bonds are delocalized over the whole ring. They're not just set between 2 carbon atoms, they're delocalized over the entire thing. So you can draw that as a circle like this to indicate that more clearly. And so the keys are that all of these carbon-carbon bond lengths are the same. All the carbon-carbon bonds are equal in length. They're all between a single and double bond. And all of the carbon atoms are sp2 hybridized. So to describe the bonding in this molecule benzene here, it's actually useful to use a combination of the 2 bonding theories that we learned. Sometimes valence bond theory is more convenient or more descriptive, and sometimes molecular orbital theory works better. And for this molecule here, using both of them together is actually kind of helpful. So to describe the sigma bonds in benzene, because each carbon has sigma bonds as well, 1 to each neighboring carbon, 1 to the hydrogen, the sigma bonds are going to be best described with valence bond theory. So if each carbon is sp2 hybridized, and I don't know why I torture myself every year and try to draw this, but here we go. So each carbon is sp2 hybridized. It's going to have a set of sp2 orbitals that form a trigonal plane like that. And then those are going to overlap. I don't know why I do this to myself every year. Those are going to overlap with other sp2 orbitals on the neighboring atoms. So each carbon is going to be sp2 hybridized. And they're going to overlap with other carbon atoms to make sigma bonds. So, oh my gosh. 1, 2, 3, 4. I'm going to probably not have enough room to do this, but we'll try. Carbon. Overlap, oh god. All right, so that was not my best ever, but not my worst either. So what you have, I'll try the carbon atoms are all here in red. I'll help that'll help a little bit.
I think you're missing one.
Oh my gosh. I need to fix this and just like have a template or something so I don't screw this up every year. All right, so there's carbon there and there, and then overlap, 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 hydrogen, hydrogen, good. Okay, so each carbon is sp2 hybridized. So you have this whole ring of sigma bonds around there between the sp2 orbitals, and then your hydrogens are out here with s orbitals that overlap with those. All right, so I think your book has a picture of this that's much better than one I can draw. Do we have any art majors in the room who can help me? All right, so anyways, that's kind of what the sigma bonds look like. They're best described with valence bond theory. The sigma bonds forming by overlapping sp2 orbitals between the carbon atoms. So each adjacent set of carbon atoms has an sp2 orbital that overlaps with the one next to it to form a sigma bond. That's the key that we're showing here. I didn't draw them in the perfect, spacing, but you hopefully get the idea. So that's how your CC bonds form. Or outside of the ring, we have an sp2 orbital on each carbon that overlaps with a 1s orbital from hydrogen to make the CH bonds. So valence bond theory is sort of a convenient way of describing the sigma bonding in this, with each carbon being sp2 hybridized, and then those sp2 orbitals either overlapping with other sp2 orbitals to make carbon-carbon bonds, or with hydrogen 1s orbitals to make the CH bonds outside the ring. So that's what we can describe. That's one way you can describe the sigma bonds. Now, the pi bonding in benzene, though, is better described with a delocalized theory, because those pi bonds, as we said, what the resonance structures tell us is that they're not localized between two carbon atoms, they're delocalized over the entire ring. And so molecular orbital theory allows us to do that. So if we remember, when you have sp2 hybridization, there's 3 p orbitals available. We've only used 2 of them for hybridization, so there's 1 left on each carbon that's unhybridized. So what each carbon atom has, if you have this hexagonal ring of carbon atoms, so let's do the carbons in red again. Carbon, 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 carbon. Each carbon atom has a pi orbital that's perpendicular to the ring, the unhybridized p orbital. And so there's going to be an unhybridized p orbital on each of those carbon atoms. That's perpendicular, and here I did include the textbook illustration to make it a little bit clearer what's going on. But then what can happen is, using molecular orbital theory, all of these pi orbitals can overlap in a delocalized fashion both above the plane where those line up and below the plane as well. So you have this sort of overlap of the pi orbitals above and below the plane where all the sigma bonds are. So in addition to the sigma bonding, you have delocalized pi molecular orbitals that are formed by overlap and mixing. Now in a molecular orbital context, we're actually mixing the orbitals mathematically, and that involves those 2pz orbitals that are perpendicular to the xy plane of the ring that they're in. Okay, so that's going to be how the pi orbitals, and again, we're not going to go into the details of that. The key is that we just want you guys to understand that when we talked about resonance in chapter 3, we talked about this idea of pi bonds being delocalized over multiple atoms. And molecular orbital theory allows us to describe that, more clearly and more accurately. So the details are not something we want you to worry about. We just want you to be a little bit familiar with that concept, that it really extends beyond diatomic molecules and can also include descriptions of bonding that are delocalized over much larger systems. All right, so that's the end of chapter 4. So we're going to have an abrupt transition next time into chapter 5, which is a lot different, but for many of you, I think will be an enjoyable one. And we'll see you guys on Thursday.